Thanks, colleagues. Good day. So I'm going to speak about the chemical recycling landscape, and um, a lot of that stuff has been covered by the McKinsey guys in the morning. So we're going to take it a level deeper. I have to remind you, though, that this stuff actually can get quite deep. It's a lot of science, it's a lot of chemistry, um, and I mean, if I had to do the whole thing, it will take the better part of half a day. Thankfully, this is a 20-minute presentation. When my colleagues approached me about a month back to tell me, okay, can you actually present this? And I thought to myself, geez, why are they coming to me? But anyway, let's give it a shot. Um, so, chemical recycling landscape, and you've probably seen quite a bit of terminology on it. So we use chemical recycling. Vincent used the term advanced recycling. We can take it a bit deeper. There's another word, it's called molecular recycling. So quite a bit of terminology. We can try and simplify this. You can actually get very deep into the science, and it really gets sort of Big Bang theory. So we don't want to get into that. But here's a very simple value chain, right? And we start off with the refinery. You probably heard the word cracker or cracking. Goes to the polymer producer, polymerization, plastic conversion, consumption, and the waste plastic, right? So as we've seen, the first part of it is mechanical recycling, right? And you produce a sort of an off-white gray pellet, right? And there's only so much you can do with it, right? But about 3 weeks ago, I've been to one of the recyclers, and I was able to see exactly how they work their system up. And they were like about, say, 4 guys actually washing polyethylene pipe. And goes into the system, they granulate it, they remelt it, and extrude it, right? There's only so much you can do with this stuff, right? This technology has advanced, and now we call it solvent-based recycling, purification. And what they've done is really a mechanical recycling process on steroids. What they do is they actually take the waste plastic, they dissolve it in a solvent, and that actually extracts the color. It extracts some of the additives as well, and you actually get a somewhat clear pellet. And you can do so much more with that, right? Now, this is what we call physical recycling. And that's really the first cascade in this loop, or the first circle in the loop, right? And it's the largest driver of the circular plastic system, as we know, right? It modifies the physical properties of the waste plastics into cleaner, more usable items. But there's one problem with this. It's the limitation, right? And I think Nikki yesterday from the Moss Group, she spoke quite a bit about it. Really didn't want to get into the detail. But the limitations are actually based on the ability to, or the inability to manipulate the molecular or the chemical structure of plastics. And that's such an important thing. The crux of plastic making revolves around the molecular and the chemical structure of plastics. We're going to get a bit into that, right? So why is the molecular or the chemical structure of plastics so important, right? I want to actually take you. We'll get into the basic processing mechanism, but I want to take you down memory lane. And this is one of the charts that I've drawn up that's actually quite close to my heart. And what it takes you back in time, and it's the price of polyethylene and how it changed with time. So from 1953, I've got it from 1953 all the way. And you can see there's a huge drop. In fact, the plastic space is about 100 years or close to a century old, right? And and you'll see some big names there. You'll see Herx, for instance, Philips. Benny is actually from Philips, now called CP Chem, right? BASF, the biggest chemical company in the world. Union Carbide, a term you don't actually hear about, but one of the remnants of Union Carbide is Univation, Dow Univation. And they're one of the biggest plastic licensors in the world. You see companies like LyondellBasell, Borealis, Ineos. You typically get Shell and BP being the oil majors, These guys have plugged a lot of money into plastics development, and we call them the plastic majors, right? Some very noteworthy things, the polyethylene was used as an insulator during World War II. And, back in the day, they actually thought that what actually turned the tide of World War II was actually carrots. That a lot of the RAF pilots were actually eating carrots, so they had good eyesight. And this is from the chemistry world. I was actually quite surprised. But really, it was polyethylene. It was polyethylene that was used as an insulator. It was actually quite light, right? And it actually made the radar systems very much more credible, much more reliable, And that's actually what turned the tide of the war. It was actually polyethylene. If not, I would have been speaking German now. Right. So Carl Ziegler and Giulio Natta, they took the Nobel Prize for Chemistry in 1963. Hogan and Banks versus Ziegler, and this was one of the largest or the longest going legal cases in the scientific community. And they fought this case on the discovery of polypropylene. And that took the better part of 3 decades. Right? And apparently I was reading, and it took in the region of about 14,000 documents. And eventually Hogan and Banks actually won this particular case, but 3 decades later. And so even in the scientific communities, you do have a bit of drama now and again, right? So, when looking at this, the major advances is technology. Catalysis, one of my colleagues were telling me in the morning, the scientists, I mean, they do so much of work in the lab and they innovate all of these things, but it's the bloody engineers that actually take the credit for it, So, I mean, you had a lot of this advancement, technology in the fields of catalysis, economies of scale, right? Plants getting bigger so that you get better cost on the product. Feedstock, you probably heard about shale gas, and there you had a lot of the natural gas liquids, ethane and propane, that actually goes to a cracker and gets cracked. I mean, with the advancement, you had efficiency changes, much more efficient plants. And one of my favorite words, integration, such a powerful word. When I actually drew up this graph, I used the context of 2 units, probably the cracker and the polymer unit. When you integrate them, you have a lot of synergies with that. But Nico mentioned in his opening address, can you separate the word petro and chem? I could write a thesis on that. Such important words. I mean, nowadays you find, the big companies like SABIC and Aramco, they're saying, okay, but why? Let's combine an oil refinery and a petrochemical facility, right? And instead of actually making fuel, let's take that crude oil and make plastic out of it. Because why make a ton of fuel from crude oil and burn it and let it go into the atmosphere when you can make a ton of plastic from it? And you can actually reuse that plastic in whichever way you actually want, right? And I mean, that was such a journey, when you look at the journey of plastics. And in these little silos, back in the day, you had these companies actually formulating new stuff. But that actually changed. The life cycle of plastics actually moved in a different direction. And that was actually caused by plastic sustainability. And that's one of the reasons why we are here all together. I mean, circular technologies, we're talking about this issue of plastics, and it's really driving the right sort of behaviors, right? So just getting back into the processing mechanism of plastics, I've actually I subdivided, so you got the monomer production. So when we start talking about monomer, we start talking about ethylene and propylene. Those are the basic building blocks into making the polymer, right? And then you've got the polymer production. And if you concentrate on that center block, you'll see the catalyst, the technology, the co-monomer, pressure, temperature. And what you do is when you put these things together, you actually manufacture a particular architecture on this polymer molecule. And that architecture, together with an additive package, will actually have different properties. So mechanical properties, processability, optical properties, and it has a range of things. And by actually working with these things and changing these things, you can get the different types of plastics. And if you look, for example, Glad wrap, I mean, it's absolutely clear. It has uniform elasticity. You've got HDPE piping that can actually compete now with a steel pipe, you know, and that's all because of the molecular structure of the plastic. I was actually just reading that the average automobile vehicle, 40% by volume is actually made out of plastics, but 10%, it constitutes 10% of the total weight. So when you start looking at the consumption of fuel, it has a huge effect, right? Got a rugby ball there, and no offense to the vegetarians, but actually the plastic ball was made out of a pig's bladder. Don't want to pee anybody off, but now it's made out of plastic, right? So the whole point of the molecular structure is to try and diversify your plastics into whatever you need. I've got this from this Plastics SA website, and fit for purpose becomes such an important term on that. Right? So getting back to the big picture view, we've got plastics recycling, and I think Nikki yesterday painted the picture of we have so much of plastics that we cannot do a lot with, and it ends up in landfills, it's contaminated. How do we actually process this? And that's when we start off with chemical recycling. One of the very foremost types of chemical recycling is depolymerization. Mainly, actually, it's targeted to PET bottles, 95% of it. And I think my colleague Martin will get a bit more into detail with that. But there's been quite a bit of advances on that front. I mean, people are actually taking the PET and they're putting it through something called an accelerated thermal oxidation depolymerization reaction, and they're making all sorts of acids and what have you with that. So that's opening up quite a lot of avenues when you start looking at the chemistry of it. The next very important part of chemical recycling is pyrolysis and gasification, right? And I think pyrolysis has been one of the sort of game changers when it comes to chemical recycling. And we'll speak more about that. And that's where chemical recycling actually fits into this big picture, right? There was a study actually done by J.P. Lang from the Netherlands, et al. And what they've done was they've simulated the Netherlands. So they took the entire waste that's produced and they said that, okay, let's try and put this through a system and try and figure out, what quantity would you be able to put through the mechanical recycling chain, or what quantities would you be able to put through depolymerization as well as the pyrolysis and gasification, just to figure out, can you actually make the circle bigger? And that sounds like a song, I think. Huh? Yeah. So, and they've simulated this. And what they've said is that when you actually do the mass balance, you find that on the chemical recycling side of it, that a large portion of it actually moves onto the pyrolysis side. And this is just a simulation based on a hell of a lot of assumptions and what have you. But this gives you an idea. It shows you that, from a theoretical point of view, chemical recycling actually is quite important. A very nice, I'm not going to go through this detail, but this is a very nice diagram I picked up from Closed Loop Partners, and it basically shows you, the mechanical recycling, the ability of it. You got the depolymerization, you get a very nice bottle out of it. Mechanical, when you start looking at polyethylene and polypropylene, when you put it through purification, you get upcycled products, but then you got pyrolysis and gasification, and that's the very hard to handle stuff. And that'll be able to absorb it and actually convert it into your basic monomer, right? So we've got a bit of a comparison here, and what we've done is we've compared two processes. That's a solvent-based recycling process with a pyrolysis process, and really it shows you, I mean, just looking at the columns there, you find that, the solvent-based recycling, it removes the color, removes the additives, but really it can't do anything with the chemical structure. Pyrolysis, you break the molecule down into its component monomer and you take it back into the value chain. Uh, Conventional pyrolysis is really easier to integrate into the petrochem facility. And that's such an important thing, integration again. You know, when you've got an oil refinery or a petrochem facility, all you do is just build a pyrolysis facility and all of the oil, the naphtha, the diesel, the gases, put it straight into the refinery. Pyrolysis is one of the most popular type of chemical recycling. I mean, you've got LyondellBasell that came up with MoreTech technology, one of the licensed technology, and it's going to be launched soon. Dow Partners with Mura technology, also pyrolysis company. On the solvent recycling side, you've got a New Cycle was acquired by LyondellBasell, another plastic major. Um, Pure Cycle Technologies partnered with Dow. And then we spoke about the carbon footprint, you know, earlier on in the discussion. And you can see, and we know it's a problem, that pyrolysis, or generally what's called the thermolysis type chemical recycling technologies, you do have higher carbon footprints. Here again, integration, and this diagram basically shows, you know, where you can actually integrate into an existing petrochem or a refinery. On the top, you've got the steam cracker, and that's one for the plastic majors. That becomes quite an important thing. If you've got a steam liquid cracker, you can put that straight in, and you would get your ethylene and propylene, and that goes back to your polymer facilities. And as you go down those blocks, you will actually see that you could get into the cat cracker, the FCC, which is a very prominent piece of equipment in a refinery, the isomerizer, the delayed coker. We've got the most preferred and least preferred, and that's really because of the yield. On a steam cracker, you get very high yield. And as you go down the delayed coker, can handle the nasty stuff, it's least preferred, right? What we also notice, you know, with the change in this particular space, in the chemical recycling space, is that you had a lot of the licensors coming in. So KBR is licensing Mura technology. You know, Lummus is licensing New Hope technology. Haldo Topso, Technip FMC, they're all licensing new technologies. And you know, when we start looking at our mass balance here, our local mass balance, you know, it shows that there is definitely room for improvement. I mean, at the moment, we're sitting on 22.9%. You know, the rest of it, I mean, the 80% of it, how do we get rid of that? You know, how do we bring it back into the circle? Or how do we make the circle bigger? And definitely chemical recycling does play a prominent role in that. And just to conclude, you know, I mean, I've been using the term make the circle bigger, and I just realized it's the name of a song, right? But what a nice analogy. I mean, make the circle bigger is making people, or make the circle bigger so people can come and actually dance in it, right? We need to make the plastic circle bigger. And the way we make this plastic circle bigger is we need more stakeholders to come in and collaborate. Right? So quite a nice analogy, I thought, when it comes to making the circle bigger. Just acknowledgements on behalf of SASL. I'd like to thank Safri Paul for giving us this opportunity. And for my colleagues, thanks very much for all of the support. I think just to leave you, you know, Dr. Roelof Botha actually, he brought up a very provocative and informative key address. And one of the things he mentioned was Adam Smith, The Wealth of Nations, he actually brought up. And Adam Smith is actually the father of economics. And one of the very sayings in that particular seminal works is actually it's not through the benevolence of the butcher and the baker that we get our daily bread and meat. I would actually like to leave you with this retrofitted thought of that sentence. It's not through the benevolence of the butcher, the baker, and the petrochemical producer that we get our daily bread, meat, and introspection. Thank you, colleagues. Thanks a lot.